Hello everyone, let's talk about another uh, computer science algorithm, breadth first search. We have already seen depth first search. There, the idea was to go as deep as possible, but here the idea is go as broad as possible in the sense that we look at our closer neighbors first, and then widen our net, and then look at their neighbors, and that instead of just going deeper and deeper. And if you look at it closely, it looks like a wave. So let's look at some of the examples. So for example, in our case, we can see that here we have this initial starting node, say S. Then we go to the next, what do you say, points in the BFS, and all of them, like we can see the next wave is like blue, and then the another next wave is like brown. Of course, this is a very simple graph just to give the idea, but this is how the BFS will look. Similarly, if we look at another example, suppose we start with this node, so this will be like label 0. But then as soon as we see that the next two neighbors are A and B, then we go to the next two neighbors, and then eventually the last neighbor, which is kind of E. So here again we see it's like it's opening up the frontiers, and then progressing the wave. This is like just another example I just wanted to cover. So suppose here we again start from 1, then next two nodes are 2, 3 marked as blue. Then it opens up the third frontier, which is like 4, 5, 6. Then this opens 7 and 8, and then eventually we reach 9, and our wave is now complete. Now, if we look at it like what does this what do you say tells about is like somehow we look at our closer neighbors, right? That's what we were initially talking about. Now let's jump into the algorithm part, like how it is actually implemented. So if you can see here, we have this initial graph which has 5 vertices or nodes in it, from 0 to 4, sorry, 0 to 4. And the idea of breadth first search is to use queue, because queue is like first in, first out data structure. And again, we will use the similar to DFS, we will use a visited set. The idea about using visited set is like we don't, because the graphs also contain cycles, and we want to make sure that we don't trap ourselves into those kind of cycles. Now let's assume that we start with so whatever we add to the queue, we will mark it as green and add it to the visited set. That means we explore, we what do you say, touch the new horizon, and then or the new frontier, and then as soon as we process the node, that means we have the traversal in BFS. So we start with node 0, we add it to the queue, and also to the visited set. Now we see that it has three neighbors, 1, 2, and 3, right? So now we will add them to the queue as well, and also to the visited set, right? Because now we have seen these three neighbors already, and now we have processed our first element, that is 0. So this will be our BFS so far, or the BFS traversal so far. Then next element in the queue is 1. So this is the front of the queue. So we always push the element in the rear and pop them out from front, or what do you say, pull them out from front. I think pop is more used for stack, but you get the idea. Then we have now 1, 0 and 1, now what do you say, process. So that's our current BFS traversal. And before processing 1, we have to see like, are there any neighbors of 1 which are not yet in the visited set? And for us the answer is yes, like it's 4. So we also make 4 part of the visited set. Then we go to 2, because 2 is the next element in the queue which we can pop out. Again, we repeat the same process, like are there any new elements, or are there any new neighbors of 2 which are not yet visited? And in this case, the answer is no, because we have already visited 0, 1, and 4. So there is no new neighbor here. Then what we will do is like, now we make 2 as process. So our BFS traversal is now 0, 1, 2. then the next element in the queue is 3, right? So we will also pop it out and see if there are any new unvisited neighbors for us. And again, the answer is no, because 3 has only one neighbor, which is 0, and it's already visited because we started from that only. So now there is only 4 remaining in the queue. And eventually we also pop out 4. There is no, again, unknown neighbor that we have not visited so far. So that means we have covered the whole graph. Our queue is empty, and eventually our BFS traversal, if you remember, is like 0, 1, 2, 3, 4. I mean, of course, it looks like there's some kind of ordering here, but no. If we start from, say, 3, the order will be totally different. So it depends on the starting node again. Uh, and now jumping to the time complexity part, it again depends on the graph implementation. So as you know, I think there are two kind of graph implementation. One is like adjacency list implementation, where all the nodes have like what do you say, list of elements. Say like this, for 0 it was 1, 2, 3, right? So it will be like a list. But in case of adjacency matrix, I think it's like we have a matrix, and now 0 can have a mapping to 1, which it's like a Boolean matrix, or you can also keep it like an integer matrix with 0 and 1. But the idea is to for like when we see the row 0 and column what do you say, 1, we mark it as true. uh, Similarly, we suppose this was a column, yeah, 0, 1, 2, 3, 4, right? Similarly, we mark it as true for for 2 as well, for 3 as well, right? Uh, Similarly, for 1, we will mark 0 as true, right? Because this was the case. But yes, like without going too much into the details, I'm assuming that you know both the implementations. So in case of adjacency list implementation, the time complexity is O of V plus C, where V is like what you say, number of vertices, and E is like what you say, number of edges. And the reason for this is like, if you see here, we had a queue in which we pushed all the vertices only once, right? But then we loop on the neighbors of what you say, the vertex that we pop out. And at maximum, all the neighbors will be equal to E, because those are the number of edges. So that's why our time complexity is O V plus E, and it's not O V into E, right? Because uh, at max we process V vertices, and for all the vertices at max we will process E edges. Not like for each vertices we are processing all the E's. No. So we are suppose one of the vertices, like one of, for example, in case of 0, it was only um, what you say, 3 edges that we have to process, right? For 1, it was again 3. But this is at maximum, because we are also taking care of the visited part, and that's why this comes up as V plus E. Yeah, and for the adjacency list, I think it's O of V squared, because now we have nested loop. And again, for each of them, we are again processing for E edges, right? And again, I think the time complexity there is O of V squared plus E. Um, so I think I hope you learned this algorithm and liked it too. And most of the time, I think the beauty of BFS is like, when we are solving some problem with the unweighted or like or uni weighted graph, like the all the weights are similar or same. In those cases, it's very easy to find the distance thanks to it, because we go to close as soon as we go to our next neighbor. We assume that our distance is 1. Then we go to the next neighbor or the next frontier of neighbors. Then our distance is 2. But I mean, once we get into the problems, I think you will get the hang of it. But I think both DFS and BFS are really cool algorithms which can help us solve easy, medium problems, and sometimes hard as well. So I hope you like this discussion. Um uh, I have shared the code and all the details in my description. Please check it out, and If you like the video and or if it was helpful in some way, please do share and subscribe, and have a nice rest of the day. See you.